All right, so we're going to talk about spontaneous processes. And when you hear the word spontaneous, a lot of things might come to mind. One thing might be something that happens instantly. When you think of spontaneity or something being spontaneous, it happens instantly. But that's not the case in chemistry. There are spontaneous reactions like when you think about uranium decaying. Uranium takes a long time to decay. We don't have to do anything to make it decay. It just decays on its own, which makes it spontaneous. But it decays over millions and millions and millions of years. Or there's a reaction of like Diet Coke and Mentos. You drop some Mentos in Diet Coke, it explodes instantly. They're both spontaneous reactions. We didn't do anything to make that reaction occur. They both just occur on their own. That's kind of what spontaneous means in chemistry. It's a physical or chemical change that occurs with no outside intervention at ordinary conditions. And ordinary conditions are things like 1 atmospheric pressure and 25 degrees Celsius. Everyday life, that would be ordinary conditions. Some energy might be supplied initially, and that's okay. Like, for example, when you're talking about lighting a Bunsen burner, for example, if you have the methane gas running, the only way it's going to combust or create that flame in your Bunsen burner is if you create a spark. That small spark is just the initial, to make the reaction get started. But once it's started, we do nothing to make the reaction continue. That we call the spontaneous process. Let's look over here at some spontaneous reactions, or not so spontaneous reactions, and we'll discuss them. So first we have methane. CH4 reacts with oxygen. This is what's coming out of your Bunsen burner. We know that when it reacts, it'll produce carbon dioxide and water. Totally okay. And actually, the net difference between the reactants and products is going to be 89 kilojoules. It's going to release 89 kilojoules of energy. So let's see if this we know is spontaneous. We've done it before in lab. But is a reverse reaction spontaneous? If we take carbon dioxide and water and combine them together, are we going to be able to get oxygen and methane gas? Well, no. It takes a lot of energy, it takes 89 kilojoules, but not only that, we have to continuously push the reaction along. So if we continuously have to force the reaction to occur, put it in some sort of have catalysts or have other things that'll actually make the reaction go without it happening on its own, we're going to call that non-spontaneous. And I know for a fact this is not spontaneous. So we're going to say, no, that's not. Let's talk about rust. We know if you leave your bike outside in the rain, or if things are outside exposed to the elements, that iron will react with the oxygen in the air and it will form rust, or iron 3 oxide. We know it releases 1,625 kilojoules of energy. So this reaction will happen without us doing anything. We actually sometimes don't want it to happen, and it happens all the time. So we definitely think this reaction is spontaneous. It will happen without us doing a thing to it. So yes, this is a spontaneous reaction. However, we can't take rust and then go back and get iron and oxygen and get our nice iron back. It takes a lot of energy to do that. We're going to push a lot of weight, lot of things to happen to make this reaction occur. It requires 1,625 kilojoules of energy. It's not going to happen. Unfortunately, once your bike is rusted, it's rusted. So I can't do anything to get that back unless I do some major work on it and in the lab or something. So if you notice a correlation here, exothermic reactions, or reactions that release energy, are spontaneous ones, but our endothermic reactions are the ones that are not spontaneous. So for a really long time, we chemists have assumed that all exothermic reactions are spontaneous, and all endothermic reactions or processes even, are non-spontaneous. But is that true? So let's go down here. What about this process? We have solid water, aka ice, and liquid water, water. So we know at ordinary conditions that solid ice will melt. If I put an ice cube on this table, it's going to melt. So without me doing anything, I can just leave it there and it'll melt. But this actually requires 6.01 kilojoules of energy. So we just disproved our whole theory there. So spontaneity is not just dependent on enthalpy or delta H. It must be dependent on something else. So let's go back and also look over here. So spontaneity depends on a combination of enthalpy, which we just discussed, or delta H, or energy, and entropy. Entropy is a measurement of disorder. There's actually a whole video on entropy alone. So if you want to learn about entropy, you might want to check out that video. The symbol for entropy is S, delta S. And so a combination of this, so we like things to be disorderly, we like things to have chaos, and we also like it to be less in energy. So a combination of these two guys, Gibbs came up with this combination to tell us if something's spontaneous or not. And he said Gibbs free energy, the amount of energy that is actually released in a system, is a combination of delta H, subtracted from the temperature that the reaction is occurring at, times the entropy or the disorder that's actually happening. So we like things being disorderly, and we also like things being less energetic. And a combination of those two things are going to make something spontaneous or not.